All right. I guess we should get started here. I'm not feeling great today. You can probably tell in my voice. I don't know, I'm a little under the weather. I think it's just sinus stuff, but anyways, I didn't want to cancel last class of the semester. So I'm going to try and work this out. I might go off camera because I've been blowing my nose all morning. So I don't want to be sitting here on camera blowing my nose, but I sent out a review for the exam. Did you all get that? Okay, so let me talk about that first. So this is the review I sent out. And as of right now, you should be able to, like in theory, you should be able to do the first 6 problems. What we do today will get you through 7, 8, and 9, and 10. And then 11 is actually just like numbers 4 and 5, finding the radius and interval of convergence. It's just a harder problem, that's all. So that's why it's a little bit further down. And then this last one, we're not going to get to this. So that problem there, don't worry about it unless you want to get bonus. So what I'm going to do is I'm going to send you an email here in the next day that'll give you a link to a couple of videos to watch. And there's going to be a few bonus problems on the test that are going to cover those videos. So if you're happy with your grade and don't really care about that bonus, then you don't need to worry about that. But if you're looking for extra points, then you can watch those videos, and then you can actually look at the homework solutions for those sections. And then that problem there should be doable. Okay? Does that make sense? Any questions? Our exam is on Thursday, right? At 1 p.m. or is it at 12:30? I need to double check. Sometimes they move these to different times. Yeah, so our final actually starts at 12:30, which is different than our normal starting time. That's just the way it's set up. So is anyone going to have any issues with that 12:30 start time? If you know that you're going to have a problem, you find out, just give me heads up, okay? Give me a little heads up. Don't tell me like an hour before the test. Just let me know. And I don't mind you coming in a little bit later to start, and I'll give you a little more time at the end. But I anticipate it will take this entire time. I don't think there's really many times in a Cal 2 class that students don't use all the time for the test. So, all right. What else? All right, let's get started then. You all ready? So we had started last time. We had talked about how it is you can take one particular function. There was this one particular one. It was 1 over 1 minus x, and how we can use that to take other functions and rewrite them using their power series. They're using a power series. But the drawback to this was that the original function had to somehow convert into this form 1 over 1 minus x or 1 over 1 minus u. If we could do that, which can be tough sometimes, then we can convert it into its power series. So I promised you that the next section we'd be able to take pretty much any function and convert it to its power series. And that's what today is about. And at the end of class, I started to talk about this, but I'm going to formally kind of present it to you now. All right. All right. So if we're given a power series, right, this is the general form of a power series. C sub n, remember, is just numbers. So if I were to write this out, we've done this many times, C sub 0, x minus a to the 0. I'm going to send you all these notes I have. Everything I do today, I will send it to you. So don't worry about copying all this down. X minus a to the first, blah, 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 blah. So the C sub 0, C sub 1, C sub 2, those are just the numbers in front of each of those powers of x. And those numbers, dictate exactly what the function is. So the only difference between two functions will be those constants. And so I told you last time that there is a way to come up with a formula for that C sub n, and I gave that to you. I told you I wasn't going to derive it, and I'm not going to, I'm sorry. But this is a super powerful formula, right? So we've seen last class that we have this formula now for the C sub n's. And that's where we get these two new definitions. The first definition is what's called a Taylor series at x equals a. So a Taylor series at x equals a is just a power series, the regular power series up here, but we're actually replacing that C sub n now with that formula and just slapping it in right there. That's it. It's the same thing we had before, but now we actually have a formula for C sub n. And if you plug in different values of n, right? If you start plugging in different values of n, you plug in n 0 here, 0 here, 0 here, you get that. You plug in 1, 1, 1, you get this one. 2, 2, 2, you get this one, right? And you can just write out the whole series. Now, remember, what does the little parentheses mean up here? Do y'all know what that parentheses means on the function?
Derivatives?
That's the derivatives, right? That doesn't mean raise it to a power, right? So this means the first one here would mean the 0th derivative, which means you don't take the derivative, which means it's the original function. And then this is the first derivative at a, the second derivative at a, the third derivative at a, blah, blah, blah. Okay, so that's the general formula for a Taylor series. And so what this allows us to do is take any function and write it as a power series. But what we're going to have to do is be able to look at all these derivatives and then plug in whatever value a is given, plug those into the derivatives. And then once we do that, we will have the power series, or what we call the Taylor series for the function. Now, in the special case that we let the x be, that we let the a be 0, which happens a lot. If we let the x be 0, a be 0, right, then we call it a Maclaurin series. Now, so a Taylor series is very general. It can be centered at any value, but a Maclaurin series implies that you're centering the power series at 0. And so what we do is we just go back into this formula and we replace all the a's with zeros. And when we do that, you get this. So we're going to take, you know, the derivative, the 0th derivative, plug in 0, and then x to the 0. And notice it's x, 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 right? These are x powers now, because the x minus a is really x minus 0, right? So that's just x. Do y'all see that? So this is what a Maclaurin series is, right? It's just a Taylor series with x being 0.
But isn't that 0 at all times? 0
Well,
over a number?
Where are you seeing 0 over a number? This right here?
Yeah.
This is the second derivative at 0. So you're taking the second derivative and plugging 0 into that.
Okay.
All right. So what is this all saying? And this is very important. That's why I put it in this red box. In order for us to ever get a Taylor series or a Maclaurin series for a function, we actually have to know a whole lot about the function. We have to know exactly what's happening to the function at a single point, whatever the a is. And we've got to know all about the derivatives there. See, because look at right here. In each one of these, right? Each one of those, that's the 0th derivative, first derivative, second derivative, third derivative, fourth derivative. I've got to be able to take successive derivatives of the function, right? And I've got to be able to evaluate that derivative at a single point. So do y'all see how that's a lot of information we have to know? Yes? But if we know all that information about what's happening to that function at one point, we can actually use that to extract information about the entire function. Okay, so this goes back to a picture I showed you all. Let me see if I can bring this up real quick. No. It's coming. Here we go. Okay, so The idea here, yeah, didn't we do cosine? I thought we did cosine. Did we do cosine? No, we did sine, but I've shown you this picture before that, so if you take the cosine function, right, and you want to know its Maclaurin series, all right, then here's what we'd have. First, let me start this at 0. Okay. First thing we do is we approximate this cosine function with a flat line, right? Now, do you all see that the flat line and the cosine function at 0, right, at x equals 0, both have the same value, right? So let's call this function, let's call it f. No, let's not do that. Let's call it g, and let's call this function f. Do you all agree that f of 0 equals g of 0? Right? When you plug 0 into both these functions, you get the same thing. It's not a very good approximation, though. So if I do another one, approximate it now instead of with a straight line, but with a parabola, now do you agree that this still is satisfied, right? They both have the same value. But what they also have now in common is that their derivatives, the slope of the tangent lines, are the same there also, okay? So it's not just the function's value is the same, the derivatives at 0 are the same, all right? And then what we do is we continue, and then we say, okay, let's make the second derivatives be the same, and that would be that function. And then third derivatives the same, fourth derivatives the same. And it's like, the more you know, the more you try and match up the derivatives, the more you try and match up the derivatives at that single point, the more it creates the entire function in both directions. Does that make sense? That's the power of the Taylor and Maclaurin series, is that the more you know about what's happening at this single point, the more you know about the derivatives, the more your polynomial that you create matches up with the original one. If I could keep going forever, of course, it would lay on top. I've shown you all that over and over, right? It eventually becomes the cosine function, right? So there's a give. I guess what I'm trying to get at is there's kind of like a give and a take here. What the? That happened to me yesterday. I have no idea what that's all about. Okay, so there's a give and a take here. Yes, we can come up with a series that represents the function, but we've got to know a lot about the derivatives. So let's do an example. We started doing one last time, or we did one last time. We did sine. I went through that very quickly. We found the power series for sine at 0. Now, at the time I did that last class, I couldn't tell you this is the Maclaurin series, all right, because we hadn't talked about the definition of Maclaurin yet. So last class, we showed that the Maclaurin series for sine of x is this. And what we did was we just took a bunch of derivatives, and then we looked at what happens when you plug 0 into those derivatives, and then we wrote out the series. We're going to do the same thing right now, okay? But let's do it for cosine, all right? So I want us to find the Maclaurin series for f of x equals cosine x. So just as a reminder, the Maclaurin series is this. It's the nth derivative of the function at 0 over n factorial x to the n. Okay, that's what it is. And I am also going to write a few of these out because we're going to be doing it. It's the 0th derivative at 0 over 0 factorial x to the 0 plus the first derivative at 0 over 1 factorial x to the first power. I'll do one more. Second derivative of this function at 0 over 2 factorial x squared plus dot, dot, dot. Okay, so I'm about to do that. So in order to do that, I need to know what these derivatives are. So let's start taking derivatives. The 0th derivative of this function is just itself, right? The first derivative of this function is negative sine x. The second derivative of this function is negative cosine x. Oh man, I can't breathe. The third derivative of this function is negative sine x. I don't know. I mean, how far we go is kind of up to us. We want to go far enough that we see a pattern or something. I know that if I do the derivative, wait a minute, hold on. That should have been what? Positive sign, right? I messed that up, sorry. Derivative of negative cosine would be positive sine. And now we take derivative one more time, we're back at cosine. So now it's just going to keep repeating itself, isn't it? It was like cosine, negative cosine, sine, cosine. So we're back to the first one. So it's just going to repeat. Negative sine, negative cosine, sine, cosine, right? So those are the derivatives. Now, because it's a Maclaurin series, I want to know what the value of those derivatives are at 0. So I'm going to start plugging 0 into these. The 0th derivative of this function at 0 would be cosine of 0, which is 1. The first derivative at 0 is negative sine of 0, and we know sine of 0 is 0. Any questions? What's this one? Negative 1. Okay, and then the third derivative at 0, sine of 0, which is 0. And then now it's going to keep repeating, isn't it? It's going to go back to what cosine was. So it's going to go 1, then it's going to go 0 again, then it's going to go negative 1, then it's going to go 0 again, then it's going to go 1, and so on and so forth. We have a nice pattern here, don't we? And this is very much like the problem we did last class. Okay, with sine, it did the same thing. So here we go. Let's start writing out the Maclaurin then. So what I'm going to do now is I'm going to start filling this in. I'm going to do this in green. Let's do that. What is that for us? So I'm going to say that cosine equals, okay, this equals, all right, the 0th derivative at 0, what was that?
1.
1.
Okay, so 1 over 0 factorial x to the 0. That's the first piece. Plus, now the first derivative at 0, which is this one right here, which is 0. 0 over 1 factorial x to the first power. Now I'll do the 2 in there. So the second derivative, the second derivative at 0, that's negative 1 over 2 factorial x squared. Plus, now we're going to have a 0 now because I'm on the third one. 0 over 3 factorial x to the third. Okay, so I've done the first, the second, 0, 1, 2, 3. The fourth one, I'll get a 1 out here. So 1 over 4 factorial x to the fourth. And I think maybe that's enough. I don't know. Do you want to keep going? I think we can stop here. Plus dot, dot, dot. Everything that had an odd power is going to go away, right? Because of the zeros up top, right? 0 there, 0 there. And then here, remember, what is 0 factorial? Don't forget, what's 0 factorial? 1, right? So that's 1. So this is going to be 1 over 1, x to the 0, x to the 0 is 1. So we get 1 out front, 1, and then that one's gone. Okay, so here, this one is minus, I'm going to put a minus out front, 1 over 2 factorial x squared. I won't have a cubed, but then I'll have a plus 1 over 4 factorial x to the fourth. I won't have a fifth, right? There won't be a fifth. It'll be gone, but I will have a sixth. Will it be plus or minus?
Minus.
It should be minus, right? Minus 1 over 6 factorial x to the sixth. And hopefully now we have enough to establish the pattern, right? The next one should be a plus 1 over 8 factorial x to the 8th plus dot, dot, dot. All right. We good?
Yes.
Now, let's rewrite that in sigma notation. And remember, we're starting at n equals 0, all right? We're starting at n is 0. So the first thing I'm going to do is I'm going to try and create this series. I'm going to realize that it's alternating. So I need to put a -1, be real careful here, to the n power. And it's n because we're starting at 0. So when you plug in 0, you get -1 to the 0, which is 1. And when you plug in 1, you'll get a -1, and so on and so forth. Okay. What about the denominators? Can you tell me about all these denominators? 2, 4, 6, 8. How are you going to generate that?
2n and then factorial.
2n and parentheses, the whole thing, factorial. Now, that will account for this first one. Keep in mind that this first one, 1 over, this is actually 0 factorial here. So we need to, these are all even numbers, and we need to start at 0. And n starts at 0. So when I plug in 0 here, I get 0 factorial. When I plug in 1, I get 2 factorial. When I plug in 2, I get 4 factorial, right? 3, I get 6 factorial. And then what about the x's? We have x to the 2nd power, 4th, 6th, 8th. And then up here in the front, even though it's not written, this is really x to the 0th power. Actually, we had it right there, right? So what should I put here?
X to the 2n.
X to the 2n. There we go. And that is your Maclaurin series for cosine. So that's exactly what I did when I graphed that just a moment ago. See if this comes back. That's what we were looking at when we did this. See the power series here? -1 to the n, x to the 2n, 2n factorial, right? And when I start, oh, I got to show it. So that right there is just me. That's just looking at just this first one. If we just do that right there, that's 1. And that's what this graph is, 1. And then I go and I grab the next one. There's the parabola. That would be if I did those 2. And then I keep going, right? All right, what do y'all think? In your formula sheets, Maclaurin series table. Here's the Maclaurin series for cosine. We just derived this, didn't we? We just derived this on our own, right there. There it is. So this table can be used, and I'll show you how we're going to use it in a little while. But on the review, notice that on some of the problems I say, like number 7, find the Maclaurin series for f of x equals e to the -2x. You must derive the formula, the series. You may not use the table. Okay, so you have to go do what we just did. Now on problems 9 and 10, we will use the table. You'll see once we get to those, okay? But if I say don't use the table, I mean you have to go through what I'm doing right now. All right, you ready to look at another one? Let's look at one a little more interesting, okay? Let's do something a little more interesting than this. So how about this? I want the Maclaurin series for this one. F of x equals x sine x. I want us to find the Maclaurin. Okay. So I don't want to have to write this every single time, but I'll go grab this real quick. This is what Maclaurin is, right? See if I can't put that in there. There we go. Okay, that's what our Maclaurin is. So we know we need to do a bunch of derivatives, right? So here we go. The zero derivative of this function is itself. The first derivative of this function is, oh man, it's product rule, isn't it?
Mhm.
It's product rule. It's the first time we've had something like this. We have to do the product rule there. Derivative of that should be 1 times sine x plus the derivative of sine x, which is cosine x, but then still times x. So I'm going to write that this way, x cosine x. I'm trusting all of you are comfortable with that. Yes. Okay, second derivative. All right, so the derivative of sine is cosine plus, but now we have another product rule, don't we?
Yes.
Okay, so derivative of that one should be, let's see, derivative of x is 1 times cosine x
Negative sign.
plus negative sine x times x, right? Negative sine x times x. So I'm going to write it this way, negative x sine x. That's the way I'm going to write it. So I hope everyone's okay with the fact that the derivative of that yellow is the blue part, right? Okay, now third derivative. Isn't this just getting worse? Oh, wait, hold on a second. Before we do the third derivative, do y'all see that we have two cosines here? Can't we put those together? Like that? Just add them up, cosine plus cosine.
That's cheating.
So there's my zeroth derivative, first derivative, second derivative. Let's get our third derivative. Third derivative. Okay, derivative of 2 cosine x is negative 2 sine x. And then be real careful here. Minus, now we have to do a product rule here, right? But that minus is going to distribute. So if we do a product on this, the negative is going to distribute through to both. So I'm going to do this like this. Parenthesis. And then here comes my product rule. By the way, what is derivative of x sine x? Didn't we just do that up here?
Yeah.
Yeah, derivative of that is this. So I'm just going to take that and like copy paste it in here. That's just sine x plus x cosine x. All right, let's clean this up. Let's clean this up. This is negative 3 sine x minus x cosine x. Do y'all see what I did there? All right, those two came together, distribute the negative to here. All right, that's my third derivative. Man, this is very different than what we had before, right? Okay, fourth derivative. All right, fourth derivative of this would be negative 3 cosine x minus, and then again, we have this in here we have to take derivative of.
Don't we have that already?
Yeah, we did that already. That was this yellow piece turned into the blue piece, didn't it? Right there.
Mm-hmm.
So I'm just going to copy paste that right there. Not even going to think about it. I'm just going to put it in. And then let me clean it up. Negative 4 cosine x plus x sine x. I don't know, maybe one more. Fifth derivative. Back to what? Back to positive here. 4 sine x. And then plus, wait a minute, x sine x, we did that earlier. That's sine x plus x cosine x. And if I put those two together, I get 5 sine x plus x cosine x. So let me come in here. Let me highlight our answers. That's the zeroth derivative. There's our first derivative. There's our second, no, wait. Yeah, that's our second derivative. Here's our third derivative. Here's our fourth derivative. Here's our fifth derivative, right? Now what do we need to do? We've got all the derivatives, but now we're doing a Maclaurin series. So what am I going to do with these derivatives?
Plug in 0 for the.
Plug 0 into each one of them. And that's because it's a Maclaurin series. That's why we're plugging in 0. So the 0th derivative at 0. Well, what do we get when we plug 0 into that? 0 times sine of 0. Isn't that just 0? Right? What happens when we plug 0 into the first derivative? So sine of 0, sine of 0 is 0. And then isn't this going to be 0? Because you have 0 times something, right? So we got 0 again. All right, let's look at the second derivative at 0. All right, here it is. So 2 cosine of 0 is 1, right? Cosine of 0 is 1. So 1 times 2, that's 2. And then minus, well, x again, x sine x, that's going to be 0. Do y'all see that when we do this, every single one of these little x sine x, x cosine, aren't those all going to like go away when we plug 0 into them? So really the only thing that really is contributing to any answer is this front piece. Do y'all see that?
Mm.
And there's a pattern to those. They keep switching sine cosine, right? The number keeps getting bigger and they're alternating signs. That's the pattern, but I'm just going to keep writing this. F3, third derivative at 0. That would be that one. That would be 0 again, right? And then I do the fourth derivative at 0, which would be -4. And then the next one, when we plug in 0 to the fifth derivative, we're going to get 0 again. Any predictions? We didn't do the work, but any predictions on what the next number would be?
6.
6. And then the number after that?
-8.
Not quite.
0.
0, then -8. And then 0, and then 10. And then 0, and then -12. Y'all see that? That's the pattern. Now, the pattern starts right once we get to this. Well, you could say it starts here. We have 0, right? And then we're going to have 0. And then what you're doing is you're basically adding 2 to that one. And then you have a 0 again, and then you add 2, you change the sign. Then you have a 0 again, then you add 2, you change the sign. Add 2, change the sign. Add 2, change the sign. Do y'all see that pattern? Now that's not really that relevant because we're just going to write this out now. Okay, let's start writing this out. I'm trying to squeeze it in right here. So this x sine x, okay, this is equal to the 0th derivative at 0 over 0 factorial. So that's this number right here, which was 0 over 0 factorial, x to the 0, plus now the first derivative at 0 over 1 factorial. Here's the first derivative at 0. We got another 0 on top, right? Plus, okay, now we do the second derivative at 0 over 2 factorial. So the second derivative is 2 over 2 factorial x to the second. Are we going to have a 3? Are we going to have a x to the third? We will not, right? Because it'll be a 0 there. Will we have an x to the fourth? We will, right? So I'm going to write this way, plus, let's see, the next number on top is -4 over 4 factorial x to the fourth. We won't have a fifth, right? But we will have a sixth. And this time it'll be positive 6 on top over 6 factorial x to the sixth. We won't have a 7, but we will have an eighth. And this time it'll be a -8 on top. Plus, I think that's enough to establish the pattern. Y'all agree with that or not?
Mm-hmm.
Yeah? Okay. I'm going to get rid of these first two because both of those are 0, right? 0 over 0 factorial is 0. 0 over 1 factorial is 0. So those are gone. So I'm just going to write this out one more time. This is, sorry, give myself a little more room. This is going to be 2 over 2 factorial x squared minus 4 over 4 factorial x to the fourth plus 6 over 6 factorial x to the 6th minus 8 over 8 factorial x to the 8th plus dot, dot, dot. Let's try and write that in sigma notation. I see a bunch of even numbers. You see a bunch of even numbers?
Mhm.
Yeah, so let's take care of this part first. The 2, 4. Oh, let's take care of the alternating. Let's not forget that. The alternating, -1 to the n, because n starts at 0. All right, let's take care of this 2, 4, 6. That's just going to be careful here. 2, 4, 6, what's that going to be?
2n plus 2.
2n plus 2, very good. 2n plus 2. See, because n starts at 0, so we need the first one to start at 2, right? We need this to start at 2, so we go 2n, that'll make it jump by 2, and then we add 2 so that we start at 2. And then x to what power? 2, 4, 6, same thing, right? Because we want to count by 2's starting at 2, 2n plus 2. And then all of that over 2, 4, 6, 8, right? Same thing, 2n plus 2, but this time factorial. That's your power series.
Are these just coincidences? How the top and the there's like a top and the bottom of this that are the same like I guess equation.
It is for this particular function, x sine x. This is just the way it is. Okay, so remember, all power series are some c sub n times x minus a to the n. This is like our x minus, or well, in this case, it's Maclaurin, but so this part right here is like this part. This is these numbers are what makes this function. So I guess it is coincidence because it's unique to this function, right? It's unique. If you change this, if you come back up here and you make that instead of x sine x, you make it like x squared sine x, that's going to change it, and it's not going to match. These won't necessarily match. I don't know if that answered your question, CJ.
It does. I was just wondering because it seemed like it was like a cheat or something. I was like, okay, maybe you could just do the same thing from top and bottom.
Yeah, no. You have to do each one because everyone's going to have a different sort of pattern. Here's the function. That is x times sine x. And let's put our series in here. Sum n started at 0 to, let's say, m. And it was, let me see if I can remember, -1 raised to the n. And then it was 2n plus 2 times x raised to the 2n plus 2. Still trying to get used to this new keyboard. Okay, divided by, yeah, I can put it there. 2n plus 2 factorial. And let's put our little slider in here and let's make it go from 0 to, let's go to 30, and let's make go up by 1, and let's go. All right, so here we go. Okay, so when we go back and we look at this, remember if we got this power series, and if we started out, the first term here is a quadratic, right? So if I just graph that quadratic right there, that's this right here. And it's pretty darn close right here, isn't it? Like near 0, it's pretty good. But the more I go out, I'm just sorry, but that never gets old to me. That just never gets old. All right.
So I guess the real trick is to get the derivative correct, because if we don't, everything else is going to be wrong.
Yeah. But at the same time, even though
Or half wrong, I guess, because
yeah, I mean, but so the beauty of this, I guess, is the fact that you just need to be able to take the derivatives of the function. Now, that can be difficult, though. I mean, that can be hard because some derivatives are going to get worse the further you go, right? They'll get more and more complicated. But for a lot of the functions that we use in math, they don't get more complicated. Now, I want to show you one more thing with this. So I want to start it over. We were asked to find the Maclaurin series for this, right? Now, let's act like I said you could use the table now. You're allowed to use the cheat sheet, okay? Excuse me. Hold on. It came out of nowhere. Whoa. Okay, so if we were able to use the cheat sheet, then what I could say is that this is equal to x times sum, n equals 0 to infinity. And then I just put the Maclaurin series here in for sign. So on our formula sheets, I would put this in right here, okay? We just did this one for cosine. In last class, we did this one, but I'm just gonna put that formula in there, okay? So it's gonna be x to the 2n plus 1 over 2n plus 1 factorial. Okay, now we can multiply, because remember, this is a sum, right? And so, you know, everything in red here is just something plus something plus something plus something. I could distribute that x through to every one of those, which means I can really just slide this x right here, get rid of it on the outside. And now let me just do one more thing. Let's put those together. If I ask you to combine those, the power here is 1, right? So you just add the exponents. So what would you get? X to the 2n plus what?
2.
2 over 2n plus 1 factorial. That's the answer. See how we didn't have to do all that work? We didn't have to do all that work. There's the answer. Now, does that match our answer?
No.
Does that match this? Wait a minute, that doesn't match. Did we mess up? No, we didn't. Please recognize that 2n plus 2 factorial could also be written 2n plus 2 times 2n plus 1 factorial. What I'm doing is I'm using the same property we used here. N plus 1 factorial is n plus 1 times n factorial. The idea being that you can always peel the first one off and then rewrite the next number down factorial. So if I go 2n plus 2 factorial, I peel the 2n plus 2 off, and then I do the next number down. So subtract 1 from this, that's this factorial, right? Y'all understand that? And then this and this cancel. The numerator and denominator, that cancels. And now you're left with the formula we had right here. Okay? So what would you rather do? If you're asked to find the Maclaurin series for this, would you rather do it this way, or would you rather use the table? Probably the table, right? The table, for sure. Yeah.
With the table, we still have to do the derivatives, correct?
No. No, look, I just got the answer. I didn't do anything. I didn't do any derivatives.
Oh, okay.
That's the great thing about the table. Okay, I want to do another one. I want to do a harder one. Okay, so this one you can't use the table because there is no Maclaurin series for this. Not on our table. The table doesn't show us formulas for everything. It shows us some of the most common ones. Do y'all recognize the first one? That's what we did in the previous class. That was 8.6. This is that geometric series. We said that, but notice we also said the radius of convergence. This only works if the absolute value of x is less than 1. Notice that e to the x, sine x, cosine x, these all have power series, don't they? And they all have a radius convergence of infinity, which means this works for any x. You have no restrictions on these. This is really nice. And then there's a few more, but 1 over x isn't here. Okay. 1 over x isn't here. Shit, hold on. We can't do Maclaurin. Do you all see why?
It's going to be infinite.
Yeah, we can't plug 0 into this. Remember, Maclaurin is centered at 0, and this function
You
isn't
would
defined
have
at 0.
0 in the denominator.
Yeah, exactly. So let me change it. Let's make this a Taylor instead. Okay, let's make this a Taylor series at x equals, let's keep it, well, we'll go 2. This is our first Taylor series. Okay, so what's going to be the difference? The only difference between this and before, what we were doing with Maclaurin, is that our formula is now this instead of this. So we're not plugging in 0 this time to the derivative, we're plugging in 2. And instead of having x by itself, it'll be x minus 2, x minus 2, x minus 2. Okay, so I'm going to grab this and I'm going to bring this over. This is a perfect example of why Taylor series are important. Because if you're trying to figure out what's going on with this function and you only have Maclaurin series, then you can't do it because it's centered at 0 and this function's undefined at 0. A Taylor series allows you to shift it somewhere else and still be able to come up with a series. Does that make sense? So let's do it. I'm going to need derivatives. Okay, what is the 0th derivative of this function? Well, don't take the derivative, right? I'm going to write it this way. Can I write it x to the -1? That's the original function. I'm doing that to set myself up for these derivatives. What's the first derivative? Why don't you take a moment, I'm gonna blow my nose and do some stuff. Why don't you list out maybe the first 6 derivatives or 5 or something? They should be pretty easy. I'm going to start listing out the derivatives. Is anybody wondering why I left mine not multiplied out? Like why I didn't do 1 times 2 and 1 times 2 times 3 and 1 times 2 times 3 times 4? Yeah, it's to It's to recognize that the fact that we're getting a factorial out there. Okay, that's a pattern that I'm establishing. So that's what the derivatives look like. Any questions about the derivatives? Now, what are we going to plug into these?
2.
2. Okay, we're going to plug in 2. So this first one's going to give me 1/2. Sorry, the 0th derivative gives me 1/2. The first derivative at 2 gives me -1/2 squared. Do y'all know what I'm doing there? I'm plugging in 2 to the -2. I'm dropping it down to the denominator.
Mhm.
Okay, almost there. Any questions on how I got any of that? Does anyone have a problem with the fact that I'm not multiplying that out, that I'm leaving everything? Is that all right with you? Does it make you uncomfortable, or are you okay with it? So there's a reason why I did that. The reason why I did it is because what we were doing in the last problems is we were just figuring out, we were just figuring out what these numbers were, right? We were just like, where the hell's my cursor? Okay, so we were just figuring out what these numbers were, right? And then we were going and just plugging them in here, right? And we were all happy and everything was great. But those numbers were nice numbers, right? 1, 0, you know, pretty clean numbers. These are getting pretty nasty. So I'm going to do something a little different here, right? Watch what I do here. I'm going to try and come up with a formula for what happens to the nth derivative at 2, because there is definitely a pattern here. Do y'all see that when we plug in 0, we get a positive? When we plug in 1, we get a negative, 2 a positive, 3 a negative, 4 a positive, 5 a negative. So we have an alternating sequence of numbers here, don't we?
Mhm.
So I can make that alternate by doing -1 to what power? I need it to start out at positive with 0 going in for n. So -1 to what?
N.
Just n. Okay. Now, ignore the positive and negative now, okay? Let's look at the numerators. 1. 1 times 2. 1 times 2 times 3. 1 times 2 times 3 times 4. 1 times 2 times 3 times 4 times 5.
They're
Right.
factorial?
They are factorial. This first one is 0 factorial. This one is 1 factorial. This one is 2 factorial. That one is 3 factorial. This one is 4 factorial. This one is 5 factorial. But if I'm doing the nth derivative, what factorial will I have here?
N minus 2.
Well, what are the n's over here? What are the powers? What are the, not powers, what are the, this is 0th derivative, I'm doing 0 factorial. First derivative, 1 factorial. Second derivative, 2
To the
factorial.
n factorial?
It's just n factorial. It's whatever that derivative is, that's the factorial that goes there, right? You'll see that? So my general formula would be n factorial. And then over what's happening on the bottom. We have 2 to the first power, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th. How is that related to the derivative we're taking?
That's the exponent?
2
Maybe
to the
plus
n
one,
plus
n
1.
plus 1?
It's n plus 1. It's, so the bottom should be 2 to the n plus 1. 2 to the n plus 1. So this is very different. I'm going to go back to when I introduced this. This was what a Taylor series was, right? I'm going to grab this whole thing and grab it over here and put it over here. Copy and pasty. Here we go. So we said, look, a Taylor series about x equals a is just this series right here. The c sub n is being replaced with this, right? Now look carefully at what this is. This is the nth derivative at a, okay, whatever that is, divided by n factorial. But what did we just, oh shit, I'm sorry. Yeah, this is right. What is the nth derivative at 2? See, that's our a, isn't it? A for us is 2 here. Didn't we just come up with a formula for that? Don't we have a formula for the nth derivative at a? For this particular problem. So instead of writing all this out, I'm going to take this and write sum n equals 0 to infinity. Now here comes that nth derivative at a. That's -1 to the n times n factorial over 2 to the n plus 1. Please understand that that's just this green part, right? That's used the wrong color. I should use something else. Please realize that this here, right, is that there, which I've now plugged in here. What still do I need to put underneath this?
N factorial.
N factorial, okay? So there's an n factorial under there from the formula. The formula I didn't show you how to, where it came from. And then next to this comes our x minus a to the n. This is a very different approach than before because we came up with a general formula for the nth derivative. Now, go ahead.
If this is the Taylor series, would the n in the sigma notation be n equals 2, or would it be 0?
0. Right. Oh, you mean right here? Would it start at 2?
Yeah.
No, it still starts at 0.
Okay.
Yeah. Now, one thing does happen here. This n factorial and this n factorial cancel. It just so happens in this problem that they cancel. You could do like, look at this as a fraction and then flip it and you'd see it goes away. So really, our series for this is this, -1 to the n over 2n plus 1 times x minus 2 to the n. All right, sorry. I don't feel like turning my video off. Okay, you good? Let's take a look at this one. 1 over x was the original function. There's 1 over x in red, right? And our thing just came out to be, what was it, x minus a, or x minus 2 raised to what? To the n, right? It was just to the n? Over, I've forgotten. 2 to the n plus 1. Here it comes. I'm going to hide it. I don't want you to see it yet. 2 raised to the n plus, can't get used to this, n plus 1. All right, okay? So when I put this here, we should see the succession of functions that get closer and closer to this. And it's going to be centered at 2, so it means it's going to start wrapping itself around this part right here. There's a line, not a very good approximation. Better line, quadratic, cubic, 4th degree, 5th degree, 6th, keep going. Right? Now, it looks like we have potentially a radius of convergence. It looks like this may not work always. Do y'all see how it's turning up real fast here?
Mhm.
So you could technically, right now, I'm not going to ask you this on a test, but I could ask you for what the radius of convergence of this is, which means you'd have to do a ratio test on it, right? Could. I'm not going to, but okay. Trying to think of what I want to do next. Let me get through what I want to get through, and then if I have time, I'm going to show you one last thing. All right, so if you're given a function, asked to find the Maclaurin series using deriving it, not using a table, you have to do all those derivatives, plug in 0, and then figure out the series, right? If you're given a function and asked to find the Taylor series, that's going to be a different formula, and you have to work through it, right? Both of them require derivatives. But what about something like this? What about if we want to know the integral from 0 to 1 of, let's say, e to the negative x squared dx? All right, so we could go, and I think I showed you this many weeks ago, that even if we go to like Wolfram and we go and try and integrate this, we're going to run into a problem. E raised to the negative x squared. We're going to get some weird error function or something like that. Yep, right? See that? Some weird error function, which means that we cannot integrate it. But we can if we use series, all right? So what I'm going to do to start this is let's find the Maclaurin for f of x equals e to the negative x squared. Now, would you would normally have to take derivatives here, right? Take all these derivatives and then plug in 0 and try and find a pattern, right? But you are allowed to use the table on the test unless I tell you you can't. Okay, so like on those problems where I said, hey, find the Maclaurin series, don't use the table. Don't use the table. Everything else on the test, you can use the table. So this is a problem like this one right here. You're integrating something that you can't normally integrate. So I'm going to find the Maclaurin for this. So what I'm going to do is I'm going to go to my formulas. I'm going to grab the Maclaurin series for e to the x. And all I'm going to do is take that formula and replace all the x's in this formula with what?
EX.
No,
Negative x squared.
negative x squared, right? That's all I'm going to do. So that will be equal to 1 plus negative x squared over 1 factorial plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial plus negative x to the 4th over 4 factorial. See, that would work. That's the way the Maclaurin series table works. All you're doing is just treating this x like a dummy, like a u, and just substituting in whatever was up here, just substitute it in here. And now let's clean this up. This is 1 minus x squared. Okay, we're going to take negative x squared and we're going to square it. What would that give me?
X squared.
Positive x to the what?
4.
4th, and then 2 factorial is 2 times 1. So I'm going to write 1/2 x to the 4th. And then I'm going to take this one, negative x squared, and I'm going to cube it. So be careful, when you cube a negative, it stays negative. So it's going to be minus 3 factorial is 6, so 1/6 x to the 6th. What's the last one?
Plus 1/20th x to the 8th.
20, is it 20? Is it 20th?
4 times 3 is 12.
24th.
24.
24th. Okay, good. 24th x to the 8th, right? That's what you said?
Yep.
And then plus dot, 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 right? So that is the power series, sorry, that is the Maclaurin series for e to the negative x squared, right? And I could keep going, but I'm gonna stop there. I'm gonna just use the first 4 terms. So what I'm gonna say is that this, I think I'll get rid of this now. This integral is approximately equal to the integral from 0 to infinity of 1 minus x squared plus 1/2 x to the 4th minus 1/6 x to the 6th plus 1/24 x to the 8th, right? And I'm just going to stop there because I said it's approximately equal to that. Now, let's just integrate these. These are easy to integrate, right? Okay, x minus 1/3 x cubed plus 1/10 x to the 5th minus 1/42 x to the 7th plus 9 times 24. I ran into, okay, what's 9 times 20? 9 times 20, 180 or 216? Is that right? Yeah, 216. So I'm just using power rule on each of these, right? Antiderivative, power rule, getting the constants. I'm just working those out in my head. And then 0, 1. So now we plug 1 in, we get something, we subtract what we get when we plug in 0, which is just going to be 0. So 1 into all these is actually real nice. It's 1 minus 1/3 plus 1/10 minus 1/42 plus 1/216. I'm going to do that on my calculator. This is equal to approximately 0.7474867, whatever, that's good enough. Well, what do you think?
It makes it easier, but how are we going to do the ones without the table?
Well, I wouldn't tell you to do something like this without the table. I wouldn't tell you
okay.
to. Yeah. The only ones you have to do on the test without the table are the ones where I specifically say on there, don't use the table. That's numbers 7 and 8. Did you just come in just a little while ago? Did you miss the beginning of this, or have you been here the whole time?
I'm here since 2:1. 2:01.
201. Okay, you missed the whole part then. Then we did the other ones by hand. Yeah.
Wait.
All right, so check this out. If I go to Wolfram Alpha now and I say integrate that, well, you know what? Wolfram Alpha is so smart. Nah, we won't even do that. Okay. If I say on 0, 1, isn't that our answer? Approximately, is that our answer? Yeah, theirs is a little bit better than ours. We stopped the first, right? We only took the 1, 2, 3, 4. We only did the first 5 terms, right? If we wanted a better approximation, we would go more terms. Now, believe it or not, this numerical answer that Wolfram Alpha is giving us, this answer right here, is being done with that same power series that we're using. It's just that the computer is going further out than we are going, because it can go way out, right? It could do the first 1,000 terms like that, because it's just arithmetic.
Mhm.
But every time, like, you know, even when you type e squared into your calculator, that's what's happening. E squared into your calculator is, so when you type in e squared, your calculator is replacing that x with 2, and it's doing 1 plus 2 over 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial. And it's doing that out, maybe the first 100 of those, and then it's giving you a decimal answer. That's what e squared is. All right. You know what's real cool about that? What's e to the 0?
1.
1. Okay, plug 0 in here. What do you get if you plug in 0 here, 0 here, 0, 0? What do you get?
0.
Yeah, no, right here. This doesn't. All those go away, right? You're left with 1, right? And e to the 0 is 1. It's not a coincidence. It better be that way, right? Here's another example. Here's sine, right? So what's sine of 0?
1.
No, sine of
0.
0, right? So plug 0 in here, right? Sine of 0, you get 0, 0, 0. So everything's 0. But what's cosine of 0?
1.
1. So if you plug in 0 here, 0 here, 0 here, you still have the 1 there, right?
Mm-hmm.
Tangent of 0 is 0. Okay. Pretty cool stuff, if you ask me. All right, we have one more thing that I definitely need to show you. And to do this, I'm going to actually go to YouTube. I want to show you a video. Now, I'm not sure when I'm sharing if you can hear my share computer sound. Let's see what happens with this. Where is he? There it is. Okay, I'm going to let you watch it. It's a minute and a half. I'm going to let you watch it first and listen, and then we're going to start it over again, and I'll translate. Ready?
I'm not happy. You are not happy with the series. How you
Can you hear it? Can you hear it okay or not?
Uh-huh.
Not understand it, but can you hear it? Yes?
Yes.
multiply the series, but let's see now some other.
Back it up.
You are not happy with the series. How you multiply the series, but let's see now some other example. What I can do? Yeah.
On there, from that first line, how did you get from the first line to the second line?
You multiply.
Show exactly how.
Well, exactly how? Let's see.
Multiply by what? 7 times what? 5 times what?
From here to here.
Yes.
Oh, you can divide one.
No, that doesn't
by
work.
one
That doesn't work.
Why not?
Could you do it manually? It doesn't work. It doesn't make any sense.
Okay, let's go further.
Why are you ignoring my question? That
No,
doesn't
no,
make any sense.
you are doing this.
You don't answer anybody's questions.
Okay, let's go continue. So, going on. It seems that you are not happy.
Do you want me to translate? Let me translate a little bit.
It seems that you are not happy.
Seems that you are not happy.
You are not happy with the series.
You're not happy with the series.
How you multiply the series, but
How you multiply the series.
let's see now some other example.
So he moves on, he gets to this point here, right here. Students are asking him how he goes from one step to the next.
From here to here.
He says from here to here. Now, do y'all see the infinite series here? Do y'all see that these are infinite series?
Yeah.
This is one minus this. It's hard to see it here. This is dot, dot, dot. Okay, so that's an infinite series. So they're asking, how do you go from this line, and that's an integral, by the way. How do you go from this line to this line? Because notice the one's no longer on top, right? It's everything that was down here is now up top, but it's different now, right?
Mhm.
Like this x cubed stayed out here, but you no longer have this division.
You took out the 1?
Well, yeah, you can take out the 1, but if you take out the 1, won't this still be in the bottom?
Yes.
And this is what's there now, but it's not even the same thing as this, right?
Yes.
This and this aren't even the same. So the student's asking, how do you go from here to here? And his answer is,
Oh, you can divide 1.
oh, you can divide 1.
Okay.
Right? And then the student says,
No,
that doesn't make sense.
Why not?
Could you do it manually? It doesn't work.
Can you do it manually? It doesn't work. Okay. And then the professor goes on to blow them off, right?
Mhm.
All right. So it does work. All right. It does work. It's you take 1 and you divide it by this infinite series. It's just arithmetic. Okay. The professor, this is obviously like, I'm not sure what class this is. Most likely, this is a differential equations class. Most likely, it could be something else, but I don't think the professor believes the student can't do the math. I think the professor believes that the student is just messing with him. I think truly in this professor's mind, he either thinks the student's messing with me or a student in this class shouldn't be asking a question that simple. Like the student needs to have known that before they walked into this classroom. Now, I don't agree with the professor's response. I think he should have addressed it. He should have said, hey, go back, look at your Cal 2, look at your, when you covered series, go and look at multiplication and division of infinite series. Look at that section. He should have directed the student a little better, but the student should have known how to do that, all right? And that's what we're about to do right now, okay? I'm gonna show you how to multiply and divide series.
I know there's cases, Professor, when teachers, they're just teaching the class and they just go by notes. And sometimes they don't know how to move from one step to another. And maybe this could be the case. He was just reading off the notes.
I would agree with you that that happens a lot, especially in the university setting. But I can assure you that the person putting the notes on the board knows the math, okay? I mean, now maybe they can't reproduce it right that second, but to them, he's teaching a bigger topic, okay? This teacher is teaching a much more broad topic to this class. This is like steps that don't need to be shown because it can be done. It's not, the task of this class is not to cover how to divide 1 by that series. The task of this class is to figure out a larger problem. So the professor definitely, I would always trust what a professor puts on the board if they're reading off their own notes, because that's pretty much been vetted, okay? Like it's gonna be right most of the time. So I like showing this video because, you know, you're gonna find yourself in a class where, number 1, there's gonna be a language barrier. It's gonna be hard to understand the teacher. It's gonna happen. You're gonna be in a class where they put something on the board and you're like, what? It makes no sense. The last thing you want to do is do what this student does and act like it's impossible math. Like that's basically what he said. It can't be done. All that shows is your complete ignorance to what just happened. And I don't mean ignorance in a bad way. Ignorance is just lack of knowing, right? So you don't want to appear so ignorant as to want to correct your professor when at the end of the day, it's just your shortcomings in math, right? So What I would suggest is if you're ever in a situation that you talk with your classmates and you'll go try and figure out how he went from that line to the next. Make that like, look, I can't go on unless I figure out how that happened, right?
Mhm.
So, okay. I did a follow-up video to this many years ago, where I actually did this problem. I finished it out just to show it is right. That's not what I'm going to do though right now. What I'm going to do is something different. We are going to try and find the Maclaurin series for f of x equals cosecant x. Now that may not seem like a very difficult problem, because we all know cosecant is 1 over sine, right? So we can rewrite that as 1 over sine. But now we run into an issue because, you know, what do? We're allowed to use the table, okay? So we can go to the shortcut, we can go to the table, we can go ahead and write out what the series is for sine. So you can go read your table yourself. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial minus x to the 9th over 9 factorial. Let me say one more thing before we move on. To Abe's point, I took a math class in graduate school called number theory, and there was only 4 students in the class, and every test was a take home, and every test took like 4 weeks to finish, right? So we had this take home, and the professor was notorious. He was a notorious professor. He was brilliant. He gave great notes, but don't bother trying to talk to this guy, okay? Like if you raise your hand during class, you're just irritating him, okay? Because you're just slowing him down. So I had this take home test, and we were it was a proof, and I was trying to prove the proof. It's like, prove this is true. And I tried to prove it, and I couldn't prove it. And I actually came up with a counterexample. So basically I came up with an example that showed that proof couldn't be true. And so it was like a proof was saying, like, remember I was talking about did I tell you about the pink elephants in the room with wings? Yeah, it's like I found a pink elephant with wings. Okay, so I disproved it. So I was like, man, you know, this is messed up, you know. And then I'm like, if this one thing in the problem was different, like it was a number, it was like if this number 5 was the number 9 instead, then the proof would be right, then it would be true. But because it's not right. So I had to go to his office, and I had to ask him, you know, I was so scared. I was like, and I'm in grad school, so I've been through some shit already. And I go in this office and I'm like, sir, the test, you know, I just wanted to show you wanted us to prove this. Here's my counterexample. And if you change that number 5 to 9, then I can do it. And here's the proof of that. And I'm like, I hand to him, he's like, oh, he looks at it and he goes, oh, that was a typo. Yeah, sorry, that 5 was supposed to be a 9. Go tell the class. Go tell the rest of the class. And I'm like, okay, so I left, you know, and I look back on that now to still, you know, to this day, and I'm like, I learned more about that one theorem. Like I learned more because of the typo than I would have ever learned had it been written correctly. Because I actually had to come up with a counterexample and then prove that. So I learned so much more by his typo. My point though, to Abe's point, is that, you know, you do want to still believe in yourself at some point, right? Like you don't want to take everything a professor gives you as truth, because everyone's human, everyone makes mistakes. It's just, you better be sure about your side first. Like make sure you're really, really sure before you say something that makes you look the way that guy, I think, looked on that video, you know? Like at least take a breath, take a day, look at it, go back. Okay. All right.
Question, wouldn't it be positive x9 over 9 factorial?
Would what be? Oh, yeah, that's a plus. Thank you. See, I was already trying to make mistakes for you. All right, so here we go. So we've got to divide this. Now, obviously, we can't split this up like 1 over this. I mean, we've never been able to do that with fractions. So we have to do what you probably don't want to do. And that is long division. And in the division box goes 1. And outside the division box goes the infinite series. Now we have to stop somewhere, so I'll stop here. All right, now just like we do with normal long division, first thing we want to do is see if there's any way we can turn that first term into this. What do we multiply x by to get 1?
1 over x.
1 over x. Okay. So now what we'll do is we will multiply everything we see here by 1 over x. So here to here, here to here, here to here, here to here, here to here. So when I do that, I'll get 1. That's this first multiplication. What do I get when I do 1 over x times this?
X squared over 3 factorial.
Okay, and it'll be minus, right? So I'm going to do it this way. I'm going to go minus x squared over 3 factorial. What would the next one be?
Plus x4 5 factorial.
Now notice I'm leaving spaces between these. Why do you think I'm leaving some space? This is x squared, x to the 4th. What if on my next line I get an x to the x cubed somewhere? Don't I need a place to line it up?
Mm-hmm.
Okay, so next one will be minus what, x to the 6th over 7 factorial. I think I'll stop there. That's good enough. All right, now we're supposed to come through long division. You come through and subtract. So it changes the signs. Minus, that minus becomes a plus, that plus becomes a minus, that minus becomes a plus. And we add straight down, don't we? I think I forgot my factorial there, sorry. Factorial, right there, factorial. Okay, add down, we get x squared over 3 factorial minus x to the 4th over 5 factorial plus x to the 6th over 7 factorial. And now we play the same game. What do you multiply x by to get x squared over 3 factorial? It'll be plus, right? Plus.
X cubed over 3 factorial.
I'm trying to figure out what I multiply x by to get this. So I need it to go from x to x squared.
X
Right.
over 3 factorial.
X over 3 factorial. Yep. X over 3 factorial. Now, if I multiply x over 3 factorial times x, that gives me the x squared over 3 factorial. And then I go from here to the next one. What would that next multiplication be? Got x over 3 factorial times negative. What power am I going to get here? X to the 4th, so minus x to the 4th, so I'm lining it up under here. And then don't I have 3 factorial times 3 factorial? Excuse me. Let's do one more there. This times this one.
Okay.
Give me plus x to the 6th over 3 factorial times 5 factorial. Now, of course, the more I go out, the more accurate this is going to be. But the whole point here is for you to understand what's going on. Are y'all okay with what's going on? Okay, minus, plus, minus, we're going to do this. Now, here's where things start getting messy. These two go away, just like the ones went away. But now we've got to put these two together. You all see that? We got to put these together.
Mm-hmm.
So I've got to take negative x to the 4th over 5 factorial, and I've got to add to that x to the 4th over 3 factorial times 3 factorial. Now, what is 5 factorial?
20,
5 4 3 2
30
1.
No,
times 10 4 is 20.
120.
What is it?
20, 60, 120.
120, okay, plus x to the fourth over, now 3 factorial is 6, 3 factorial is 6, 6 times 6 is 36. And now you have to get a common denominator. Does 36 go into 120?
Yes, 20 times.
Uh,
I mean, 6 goes in there, so
what?
never mind. I have a brain.
What is the common denominator here?
6,
6.
60.
Least common denominator.
Oh, least.
Probably like 720 or something like that.
Yeah, it's probably a pretty big number, but you got to you got to put them together.
Wouldn't it be 360?
Or yeah, 360. Yeah,
360
sorry.
is probably the better one. Yeah, it's okay. I mean, no matter what, you got to put these fractions together, right? This is back to like algebra, pre-algebra stuff. Now it's not fun, but okay, I'll multiply top and bottom here by 3, top and bottom here by 10. That should get it, right? So negative 3x to the fourth over 360 plus 10x to the fourth over 360. Now I can put them together. That gives me 7x to the fourth over 360. And I believe that's reduced. We can't take that any further. Yeah, so that's it. So that's what happens when you add this down. 7x to the fourth over 360. And do you see how you would have to do the same thing for this? Right?
Mm-hmm.
No, I'm not going to do that. I'm just going to say, I don't know what that is. Who cares? Because what would the next, with just having this first one here, couldn't we figure out what the next piece up here would be? What would it be? How do I turn x into that?
7x cubed
Mhm.
over 360.
Over 360. And then I'd have to play this game again. Right? Okay, now, if you go look at the test thing I gave you, the review, I say find, number 9, find the first 3 terms of the power series for f of x equals 1 over cosine x. We just did 1 over sine x, didn't we? Didn't we just do 1 over sine x?
Mm-hmm.
So what we just did here is what you'd have to do on that problem. 1 over cosine x, right? You have to do this, write the series, the Maclaurin series for cosine, and then do the division, and you only want the first 3 terms. That's why I didn't keep going here with more of these, is because I only want to be able to get the first 3. Okay? So I'm going to go back to Wolfram alpha, and I'm going to type in cosecant x. And I'm willing to bet that Wolfram alpha is going to give me the series for that. 1 over x plus x over 6 plus 7x cubed over 360.
Wow.
So we had, right? So if you wanted to integrate this, right? If you want to integrate that, you'd use this. Even better, watch this. What if I now, knowing what we know now, what if I asked you, I'm not going to ask you this, but what if I asked you to integrate e to the negative x squared times cosecant x dx?
Isn't that integration by parts?
Well, you're not going to be able to do it. It's not going to work. This is too complicated.
We
Now,
have to substitute the cosecant
I'm glad you're
one.
thinking that, but didn't we do e to the negative x squared a minute ago?
Yes. Is it like a product
Maclaurin
of
series for it?
Yeah, don't you multiply the power series together?
Yeah, so if I had, imagine I have this. This is, copy, that's e to the x negative x squared, that's that. So imagine taking that and multiplying by cosecant x. Now, what's the power series for cosecant x? Well, we have the first 3 terms. There they are, right? Now, if I just do like a FOIL, I'll do this times this, that's 1 over x. I'll do this times this, which is just x. This times this, which is Okay, now what I would do is I would do this one distributed. What's that?
Just x, negative x.
X. Okay, this times this. Negative x cubed over 3 factorial. This times this.
7/20.
X to the 5th, right?
Yes.
360. And then I could keep going, right? I could do another one. But see, with power series, you're always doing an approximation. You're always going as far as you need to go. So then what you would do here is maybe, you know, collect like terms, or you just integrate that, okay? Just do power rule. All right. Well, we are almost out of time. So let's just look through this review again. Rewrite as a rational number, as a fraction. So this involves a repeated decimal. Okay, we did that geometric. That's a geometric series. It converges. Here's a telescopic series. Find the sum. That's the key. That's telescopic. This one, you have to rewrite this first in sigma notation and then figure out if it converges or diverges. And to do that, you're going to use some method. I don't know. Something from 8.4 or 8.3 or 8.2. Maybe it's the integral test. Maybe it's the not intern test. Maybe it's the comparison test, limit comparison test. I don't know. It's up to you. Numbers 4 and 5, you're going to find the radius of convergence, interval of convergence. So you're going to do the ratio test there. And you might have endpoints to test on those. And you might not. It just depends on the problem. Number 6, find the power series. For that one, you need to make that look like, you need to be using this. Okay, so we did a problem like this. Okay, we did a problem like this in class last time. I think. No, time before that. Well, when was it?
Tuesday.
We did do it, right?
Yeah.
There it is, like this one. See, x cubed over x plus 2, we did that. Very similar to this one. X cubed over 2 minus 4x. You just have to kind of make it look like that. Find the Maclaurin series for this without using the table. So you have to do your list of derivatives and then plug 0 in and then find your series. Number 8. That's very much like the one I did a second ago. We did 1 over x at a equals 2. This is 1 over x squared at a equals 2. This one we just did 1 over sine. I did this a second ago, but I did e to the negative x squared instead of cosine of x cubed. But you'll use the table. You'll plug in x cubed into the cosine series and then just integrate term by term. All right. That's what the test is going to be like.
And we're expecting 10 problems, 8?
Somewhere in that neighborhood, yeah.
And how long do we have to have for the exam?
You have from 12:30 to 3:15, I think.
And this is just going to be on chapter 8, right?
There's going to be one problem on the test that I do not have a choice. I have to put it on there. The whole math department has to put it on there. And I can tell you that it is a volume, solid of revolution. Let's do this. You'll have all your formula sheets, right?
Mm-hmm.
All your formula sheets. I'm going to also allow you to make your own formula sheet. Okay, just one sheet of paper, front and back. You can put any steps or procedures or other formulas that you think you might need, anything else. You just cannot have worked out problems on it. Okay, so you can't just work out a bunch of different problems and squeeze them onto a piece of paper. Steps, procedures, hints, formulas, fine. Worked out problems, not fine, right? And everyone will be showing me their thing like this before the test.
So the formula sheets that I already have, can I just write, like, if I really just wanted like the formulas for like the volumes and surface areas and stuff, can I just write that on the back?
On the back of what, your
The
formulas?
formula sheet that I usually use for tests.
Yeah, that's fine.
Okay, cool, thank you.
So technically, we have a week to master chapter 8.
You're lucky. My my Monday, Wednesday class, their test is on Monday.
Ooh,
Yeah,
Oof.
we just finished this yesterday.
wow.
Yeah.
That usually happens to me like every semester. I'm actually kind of blessed on this one.
Yeah. So next week, my office hours will not be normal office hours. It's just the way things go because things overlap. And so I will be sending out an email to kind of give you an idea of when I'd be available next week through Zoom. And I apologize if it doesn't work out with your schedule. There's not much I can do because it'll be working around my schedule.
Now, as far as the YouTube videos that you have, is there examples like the ones we just went over to
Yes.
practice?
Do the homework problems from those sections from 8.7.
Okay.
Taylor and Maclaurin series. There are plenty of problems that are going to be like that. Yes.
So in the 8.7, I saw there are like 2 parts of 8.7, A and B.
Yeah, that means there's a lot of problems, or it took me a long time to do them, I guess. You're talking about with the homework solutions?
Yes, sir.
Yeah, that means that there's probably a lot. Let me see. Okay, I'm going to be working out. Going to be obviously not working out. Okay, so 8, 7, yeah.
So you always wrote focus on the whiteboard to focus the camera, or
Yeah.
for us to focus?
Both.
Okay.
Both. No, I focused the camera on the focus and then locked the focus so it wasn't always trying to adjust to me as I'm walking around.
I see.
Yeah. But it kind of works both ways. Okay, so class is like officially over. You're welcome to leave. I'm going to show something else. You're not going to hurt my feelings if you leave, but if everyone leaves, I'm leaving also. There is, and this won't be like a bonus question or anything like that. This is really purely just for like your own kind of exposure to something cool in math, all right? So feel free to go if you want. This is going to take me about 10 minutes to do. There is a famous equation in math you may or may not have ever seen, and this is it right here. E to the I pi plus 1 equals 0. This is a very famous equation, and certain mathematicians and people that ever see it say that it's the most beautiful equation in math. And that beauty is subjective, right? So we're never going to agree, or, you know, we're never going to come to a final conclusion as to whether or not this is the most beautiful equation in math, but a lot of people think it is. And the reason they think it's the most beautiful equation in math is because it contains some of the most important numbers in math. First, 0, which I know 0 seems like not a big deal, but all of our numbers in our number system have to have a certain, our number system has a certain structure to it, okay? Our number system is called a field, and there are 12 axioms that make a field a field. And one of the axioms is that every field has to have what's called an additive identity. So it has to have something in the set of numbers that when you add it to other members of the set, it doesn't change them. And we know that that's the way 0 works. Anything plus 0 is still going to be that anything, a plus 0. So 0 is the additive identity in our number system. 1 is the multiplicative identity in our number system. A times 1 equals A. That right there is actually important. It's hard to imagine that that's very important, but it is. The multiplicative and an additive identity are required to make up a field. Then you have pi. We all know pi is really useful when it comes to circles. We know E is that special base that when you look at e to the x and you graph that function, that is the only function that is equal to its own derivative. There is no other function that behaves that way. So that base e 2.718 is very, very special that it works out that way. And then of course I, do we all know what I is?
Imaginary numbers.
Imaginary unit. I, by definition, is the square root of -1. That's what it's defined to be. And if I is the square root of -1, I'm going to save myself a little time here. If I is the square root of -1, then if you square this, if I square the square root, the root goes away, I get -1. So I squared is -1. And then if I cube I, that means I'm going to take I squared, which is this answer, and then multiply it by I again. I'll get -1 times I, so I get -I. And then if I take that and multiply that times I again, I'll do that, basically becomes I squared and I squared, which gives you 1. Then if I hit that with I again, I get I. So what happens is you start at I, you hit it with another I and it becomes -1. You hit it with another I, it becomes -I. You hit it with another I, it becomes 1. Hit it with another I, it goes back to I. And then it repeats. So it's what we call cyclic. Starts at I, hit it with an I, it becomes -1. Hit it with an I, again, it becomes -I. Hit it with an I again, it becomes 1. Back to I, back to -1. So it's almost like -1 to the n. You know how -1 to the n is either going to spit out 1 or -1?
Mhm.
I to any power is going to spit out one of these 4. Okay? So it's the imaginary unit. It's very, very useful. All right? That, believe it or not, imaginary numbers open up many, many doors for us. So I'm going to now show you that this equation is true. All right? I'm going to show you that this is a true equation, which means that what I really need to show you is this. E to the I pi equals -1. Do you all agree that if I can show that that's true, then you'll be convinced that this equation is true?
Yes.
Because I'm just subtracting 1 on both sides, right? Okay. So that, I'm going to try and show you that right now. You ready? Here it comes. So I'm going to start off with e to the I pi. What I'm going to do is I'm going to write it using its Maclaurin series. So what's the Maclaurin series for e? Let's go look at that. Here it is. E to anything is 1 plus that anything over 1 factorial plus that anything squared over 2 factorial plus that anything cubed over 3 factorial and so on and so forth, right?
Mhm.
So I'm going to do that now. This is going to be 1 plus that anything, which for us is I pi over 1 factorial plus I pi, that quantity squared over 2 factorial. I've got to do quite a few of these. I pi to the 3rd over 3 factorial plus I pi to the 4th over 4 factorial. I pi to the 5th over 5 factorial. I pi to the 6th over 6 factorial. Let's stop there. That should be enough. All right, now that is equal to 1 plus, let's go ahead and square these things. That's I pi over 1 plus, let's see, what happens if I square I?
You get -1.
Yeah, so I'm going to bring this back here. Let me bring this here just so we can remember how this is going to work. Copy, where is it? Paste. So this is I, this would be I squared, this would be I cubed, this would be I to the 4th, then this would be I to the 5th, I to the 6th. Make sense? I to the 7th. We just keep going around. So I squared, that would be -1. So let's change this to a minus. And then I still have to square the pi, don't I? Pi squared?
Yes.
Over 2 factorial. And then let's see what happens here. I have I cubed. What's I cubed?
Negative I.
Negative I, isn't it?
Yeah.
Negative I. So I'm going to go negative, and now I still have an I there, but then I have a pi cubed over 3 factorial. Okay, now I to the 4th. I to the 4th is 1, but I still have a pi to the 4th on top, and then 4 factorial. Then I have I to the fifth. What's I to the fifth?
I.
I, so it's going to be I and then pi to the fifth over 5 factorial. All right, now what's I to the sixth?
-1.
-1. So this is going to become minus pi to the sixth over 6 factorial. Okay, and this continues, right? Yeah.
Mhm.
All right, so now what I'd like to do is I'd like to focus your attention on everything that does not have I in it. And I'd like to write those by themselves. 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus pi to the 6th over 6 factorial. Now, plus it would continue, right? I would continue to have things that don't have I in them, right? Out here.
Mhm.
But I'm just going to stop there and say dot, dot, dot. Okay, I'm taking all that and then I'm adding to that everything that does have an I. That has an I, that has an I, that has an I, and there's another one that has an I, right? There's a bunch of them. So what
Basically
am I doing?
all odds, I guess.
All odds, yeah, yeah, exactly. So since they all have I's, can I just factor an I out of each of those?
Mhm.
Okay, so if I factor an I out, then I'm going to be left with, let's see, pi over 1 minus pi cubed over 3 factorial plus pi to the 5th over 5 factorial. And the next one would be pi to the 7th over 7 factorial, even though I can't see it there, plus dot, dot, dot. All right. Who can tell me what this is? That is the Maclaurin series for something.
Cosine?
Cosine. Cosine of what, though?
X.
Cosine of what?
Pi.
Cosine of
Pi.
X.
Cosine of, so cosine of x is this, right? But we have not x's. I hear someone saying it. It's
Pi.
It's
Pi.
pi, right? This is cosine of pi. It's just all those x's replaced with pi's.
Which is a 0.
Not 0.
Oh, -1.
This is cosine pi, right? Plus I times, now do you recognize that?
That should be sine
That's sine
of
of pi.
pi.
Okay, now, what's cosine of pi?
1.
-1,
Oh, negative.
right? What's sine of pi?
0.
0. Okay, so what have we shown?
-1.
Pi equals -1, which is what I was trying to show.
Huh.
What's really kind of cool though, I mean, that's cool already, all right? You should be happy about that. But if you replace this pi with x, okay, just replace the pi with x, then this becomes x, 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 and then this becomes cosine x and this becomes sine x. And you may remember in pre-cal, maybe, seeing a theorem that looked like this, where it was like cosine theta plus I sine theta was a way that it was called Denmarvae's theorem. I know I'm saying that wrong. Denmarvae's theorem. I'm screwing that. Hold on. I don't know. Maybe this looks familiar. Maybe not. From college algebra or pre-cal. If not, don't worry about it. But if you had seen it before, then you know. Yeah. So this is a very, very useful identity. But yeah, that's about it. So anyways, I'm done. That's going to wrap it up for our semester. So I do want to just say that I appreciate, you know, all of your participation and all of your, you know, leaving your videos on and being engaged in the class. I know this has been hard for all of us. I mean, I think we would agree that there's pros and cons to this, right? Like we can all just get up and walk and continue our day with whatever, but there's something that's getting lost in us being remote also. But I appreciate all of your participation, and you know, thank you for that. It made it a lot easier for me too. And down the road, whatever happens, you know, future classes, my door is always open to you in terms of, you have my cell phone number. Feel free to reach out and contact me. I still talk to students that are way past, or, you know, they've got their degrees already. We still keep in touch, and, you know, I do help students out as they move on too. So don't ever feel like you can't reach out to me. I just spoke to a former Cal 2 student like 3 days ago, who's at A&M right now. And he was telling me how his semester went and everything. So feel free to keep in touch. And thanks again. And I'll see you, if not before like next week, office hours or something like that. I'll see you at the exam. Any questions or anything? No?
So we don't have class on Tuesday, just being super sure.
Yeah, no, we do not. We
Okay.
do not.
And did you get that file I sent you on chat?
I didn't.
Oh, you didn't? What?
Well, no, I didn't look. I didn't see
Oh.
that it came through. Is it a virus?
No. In the homework video for one of the homeworks, you said you'll give us bonus points for that.
Oh, yay. Okay, great. I think it downloaded. You know what? Do me a favor. Can you send it through email just in case this doesn't come through right? Will you do that?
On Canvas, you mean?
Yeah, on Canvas. I mean, not
Okay.
right this second, just before the final. That way I have a record of it, and it's usually
Also,
better.
I have a question. You never posted the quiz 2 grade.
Yeah, I remember that too.
Yeah, I realize that, yeah. So what I'm gonna do is I'm basically gonna just give everybody I'm gonna go back, you know how I've called on people in the past? Just gonna kind of go back and look at all that. And pretty much everyone there's only a few students that I called on multiple times that didn't answer. Like, and then I would end class and they would still be there on the video, like they didn't even know what class ended. So there's only like 1 or 2 students that wouldn't get full hundreds for all the quizzes, but everyone else is just going to get hundreds for those 5 quiz grades, just as a participation grade.
Let's go.
Oh, wow.
Yeah,
Thanks.
yeah. So,
Ouch. All right. Thank you.
okay.
Push that.
Except for you, Mustafa. I'm just kidding. See, I know like everyone who's still here, like I pretty much know by first name now. So that's a good thing. All right. Thank you. Y'all have a good one. I've got to go.
Thank you very
Thanks,
much.
Professor.
You have a good
We'll see you at the
2 year.
final.
Thank you, sir.
I don't see
See you at the final.
Good luck on your other finals.
Thank you.
Thank you.
Thanks.